So, thank you for coming back to MLF. Hope everyone had a good reading week. How many of you guys are done your midterms? Are done your midterms? Wait, what? How many more midterms do you guys have left? One, two. I see three. What program are you guys in? I'm just curious. Since we have a small group, I'll just like do something. Yeah. Yeah, like what program are you guys? CS? CS? Anyone in Eng? Nice. Anyone in Eng? Are you core 8? Are you first year? Ooh, ECE? Hmm? Camp, nice. Okay, well, I'm just glad you guys are here. At first, I was kind of scared that no one's gonna show up, but thank you for coming. So, compared to previous weeks, we're not gonna do a recap. Reason being that we're gonna take a detour away from neural networks for now. So, I'm sure you've heard of decision trees, right? It's a very classical machine learning algorithm. I personally think it's the most fun one because it's very related to what we do on an everyday basis, and it's also one of the easiest to understand. And one of the main reasons you would use random forest, or sorry, decision trees is that it is very lightweight, right? You guys remember from neural networks, there is lots of matrices, lots of mathematical calculations, lots of gradients, right? You don't have to do any of that with decision trees and random forest, and that's why we're gonna look into it. So let's start off with a warm-up activity. Should I study for my midterm tomorrow? So this might be a typical decision tree that you may think about when you study for midterm, right? So is the midterm tomorrow? No. Well, if it's not tomorrow, did you attend your lectures, right? If you did attend lectures, okay, I'm just gonna procrastinate. You get the point of this, right? Did you play Clash Royale during lectures? If you did play Clash Royale during lectures, okay, lock in, keep studying, but yada yada, right? So you might be asking, well, why am I going through this? Well, that's exactly how decision trees in ML work as well. Except now, instead of asking yourself, did I play Clash Royale during lecture? You will be, sorry for that, you will be looking at something called a decision boundary. And don't worry, you're going to learn more about what that is in the future slides. So, anyone have any questions before I get into the details of decision trees? Everyone good? Yeah.
Why do we use decision trees?
Yeah, so decision trees, they're very lightweight and they're very easy and intuitive to understand. And computationally, they're not expensive, right? Were you here for like week 3 and 4? Yeah, you recall that you do have a lot of matrices, right? A lot of numbers, right? In random forests and decision trees, there's no such thing. The math is so much simpler. And why that matters is the more calculations you need to do, the more resources you need, right? We don't have infinite hardware or infinite like GPUs to do all these things. And when you train bigger models, right, with matrices, it takes a long time. So sometimes you don't always have to do a neural network. You can choose a more simple algorithm. Hello, welcome. Yeah, so what are going to get out of today? You're going to learn 4 key concepts about decision trees. First of all, decision trees. Second of all, entropy and information gain. Third is random forest. Random forest is essentially a spin-off of the decision tree algorithm. And also you will learn about ensemble learning. So let's start with some decision tree basics. So recall graphs, right? Who here remembers the word graphs from the previous MLF? Yep, so a tree is a special case of a graph. They might not have gone over this in previous weeks, but it is a connected and undirected graph with no cycles. So that definition, you don't really have to care much about. You just need to intuitively know what a binary tree is. So a binary tree is when a parent has at most 2 children. So is everyone clear on what a binary tree is? If you have a point, right? At most, you can only have like 0, 1, or 2 children. So make sense? Can I proceed? Okay, so there's a lot here, but I will go through these one by one. So decision tree basics. First of all, you have a node. So a node is a block in your decision tree, or back in this diagram, a dot on the decision tree. In decision trees, a node can either be a decision boundary or a prediction. So what are those terms? let's look at this decision tree here, right? Let's say I have a vector. You guys know vectors, of course, right? Of x, y, and z coordinate. And I want to know if it's class 1 or class 2. So what's going to happen is I have this vector, and I'm going to look at, for example, let's say I have the vector 1, 2, 3, right? Keep that in mind, right? X is 1, y is 2, z is 3, right? I'm going to start at the top of the tree, right? So is 1 less than 10? Yes, right? So you go left. Is 1 less than 4? Yes, as well. You go left again. And you reach that prediction of class 1. So essentially what happens is if you have like a vector, right? You just have to walk through this decision tree until you reach the end. Does that make sense? Does that make intuitive sense for everyone? Before I get into, yeah.
Is it you set the decision boundary like x less than 10 or?
I'll get to that later. Yeah, so let's just say magically we have these boundaries for now, but don't worry. I'll get into how those are decided. So now more important terminology, an internal node. So an internal node is when you make a decision. So in this tree here, you see those blue blocks, right? Those blue blocks, if you can't tell, is a decision you have to make, right? If your value is, for example, less than that or greater than that, you'll have to go either left or right. Does that make sense? Can I have a thumbs up if it makes sense? Or at least or a nod? Okay, so next are leaf nodes. So in graphs or trees, a leaf node is essentially the bottom node in a tree, right? So a leaf node by definition has no children. But in the case of decision boundaries, this is when you make a prediction. So in other words, you have walked through to the bottom of the tree, right? So for example, in our vector of 1, 2, 3, right? You walk through the decision tree and you get to class 1 over here, right? That is called a leaf node, and that's going to make a prediction. Can I move on? Okay, so some more mathematical things. The internal nodes, or this decision, it partitions the input space into axis aligned regions. I only use that because it's the proper terminology, but you might remember in math, right? Let's say I have a real number line, and I have this condition of x less than equal to 10, right? That splits it into two parts, right? You have a bunch of values that are less than equal to 10, and a bunch of values that are greater than 10, right? So that is exactly what a decision boundary is. So I don't want to explain more because it is better if we go through a visual example. So there might be a lot to uncover here, but on the right here, let's look at the table first, right? On the table, we have a data set of fruits, right? You have a bunch of apples and you have a bunch of oranges, right? Each fruit has their own height and weight. I know the values are not realistic, but this is just for the sake of our calculations. So is everyone clear on what the graph represents? The graph is essentially, so you know how you have each fruit, right? Each fruit has like a weight or a height. We're just plotting it onto a grid for now. Is that clear? Yep. So when we plot it onto the grid, let's say I also have this decision tree that I have. Ignore all the brain rot in the slides. But let's say I have a fruit that has a weight of 6 and a height of 7. So I will give you guys just 30 seconds and you guys tell me what fruit that is by walking through the decision tree. So what is the fruit?
Or
Orange, yes. And how did you reach the conclusion of orange? Like, walk me through how you walk through the decision tree.
the height is less than the height is less or equal than 9.5.
Yep.
So it's true.
Yep.
But the weight is false because 6 is less than 6.7.
Yep, exactly. That is how you will walk through a decision tree. So I have another example here, but I think we're pretty clear on what is happening, right? Does anyone still want me to go through this one or no? I mean, you can just do it in your head really fast. So it's gonna end up being an orange as well. Wait, yeah, orange as well. But more importantly, right? You see this decision tree here, right? You see there are three decision boundaries, right? There are three places where we make a decision. Now, usually we won't actually be able to draw out this tree, but you'll be able to actually visualize it. There's a reason why we call this a boundary. Look at that again. That is the exact same graph we had, except I just added the decision boundaries into the graph. Does it make sense? Right? For example, back here, height less than equal to -5. You see here, we make a partition here, so it splits it into a few categories, right? The same thing happens with the rest of the boundaries you have here. So what actually happens then? Well, internally, the decision tree just splits this input space into many partitions. So what's going to happen is, let's say I have a new fruit, a brand new fruit, right? I don't know what it belongs to. It has some weights or some height, right? And it's going to fall into one of these like grids here, right? You see how the grid is like split into five, right? Split into five. Let's say it falls, you can see my cursor here, right? Let's say it falls here, right? The decision tree is going to predict it's going to be an apple. Does that make sense? Yeah. Yeah. So I was going to say, what do you notice about these partitions? These partitions all predict a single class. That is the ideal goal that we want. There's, of course, a catch to this. That is ideally what we want. We ideally want to split our current data set into these partitions so that when I get a new fruit, I can be confident in saying that it's an apple or orange. Yes.
Does it generalize as well? Because it seems that it can overfit a bit.
Yep. We will, thank you for pointing that out. That is one of the actual main issues with decision trees, and it'll actually be tackled by random forests, which I will get into later. So yeah, if you missed it, if you can't, maybe if might not be quite obvious. It wasn't obvious to me when I first learned it. This can really easily overfit to a data set, right? So there are ways to tackle this, don't worry. But is everyone clear about what's happening here? Any questions? Okay, so just one more side note. With a decision tree, you can either have a classification or a regression tree. So a classification tree just predicts a discrete outcome, right? So we were predicting whether or not it's an apple or orange. That is classification. You can also do something called a regression tree. Unfortunately, we don't have time to go through that right now. But if you're interested, you should look that up in your free time. Essentially, think back to linear regression. It just predicts some numerical value for something. I'm not going to get into it in too much detail because we're just going to focus on classification trees today. So are we good to move on? Thank you. So back to your question then, right? Do we hard code these decision boundaries? No, this is machine learning. We need something systematic, right? We need to tell the machine to how to systematically find the best splits. So how can we do that? We do something called entropy. Entropy is all about making better splits with your decision tree. So if you recall from week 1 to 4, right? We always try to determine how good or bad our model is, right? And we used a loss function for that. Does anyone remember that, or does that ring a bell? Yeah, what are some common loss functions?
Cross-binary entropy.
Yep, cross-binary entropy loss, mean square error, all of that, right? So in the context of decision trees, we want to make sure, or we want to see how good or bad a decision is, right? And I just want to give you guys 30 seconds, right? Let's say I have a split. What does a good split look like generally? And what would a bad split look like? Is an open-ended question is meant to be like that. Let's see online. So any ideas? Yep.
You could split all the oranges or all the apples and no, or in a single part of the split.
Yep.
There is only apples or only oranges.
Yep. So he nailed it. So a good split, right? When you make a decision, right? You want to be clear about something. So if you're given a fruit, if you're given a bunch of fruits, you ideally want to be able to split it so that one side is all apples and the other side is all oranges. So here is another example I can go through. He basically nailed it, but let's look at this example here, right? We have a new data set. I don't know why the apples are blue. That was my bad when I made the grid. But let's say you have a bunch of apples and a bunch of oranges. Let's say I split it like this and compare it to this split. Which split is better? I will flip-flop between the two. This is the first one. This is the second one. This is the first one, this is the second one. Which one's better?
Option 2.
Yes. Now, why is option 2 better?
The upper part, there is only oranges, so
Yeah.
it's split.
Yep.
The option 1, there is apples in both sides, so both sides are not good.
Yep. So, does everyone agree with that? Right? Clearly, this split is better because the split on the upper half splits it to only oranges, right? Meanwhile, here on both sides, you still have both apples and oranges. So option 2 is the better split. So in math terms or fancier terms, we want to think a split criteria that reduces as much uncertainty as possible. This is going to give us a larger information gain. These are going to be big words we also define later, so don't worry. But I feel like the English word itself gives you quite a bit of intuition as well, I think. Are we good to move on? Any uncertainty, I guess. That wasn't meant to be a joke. So here's where we introduce entropy. So entropy is a measure of uncertainty in its possible outcomes. This is just a mathematical formula saying that the entropy is the probability of each class times the logarithm of the probability and sum it up. Don't worry, I'm going to walk through an example because what's the point, right? So we're back to this fruit data set, right? We can all agree there is 3 apples and 4 oranges, right? So to just compute the entropy, this is what I'm going to do. For every class you have, so we have 2 classes, right? We have apples, we have oranges. So there is a 3 out of 7 chance that something is an apple in here. So you will plug that into your formula, right? 3 over 7 times log base 2 of 3 over 7. You do the same thing. Does this make sense? Does the math make sense? Does it make sense what numbers we are plugging in to here? Yep. So our entropy is therefore 0.9852. So how do we know that we're more certain about something then, right? You look at this number and you go like, okay, well, how am I supposed to interpret a number called 0.9852? Well, if the split produces more pure groups, right, like what you said before, then the outcomes within each group should be mostly one class. So if you look back at this formula, right, let's say in your group, you only have one kind of fruits. What is going to be the value of this expression?
P of x will be 1.
Yep, P of x is 1. Therefore, what is the entropy? If the probability is 1, right, and you take the logarithm, yep, 0. Yep. So if I have a group of fruits and they're all oranges, right? You can all agree the probability of an orange is 1, right? So if you put that into this formula, you put the 1 into the log, it's going to get you 0. So the goal is that the lower the entropy is, the better the current group you have. You might have a lot of questions thinking, well, what am I supposed to compare this to, right? But don't worry, I'll get into that. Yep.
We check the probability of only one class or both classes.
Both classes. So you'll get into, so right now it's confusing, right? Because I just have this data set and I just get this number, right? But keep in mind in a decision tree, right? This data set, do you agree that it's going to split into smaller subgroups when I make a decision? Right? So don't worry, I'll get into the example, but it's great that you have these questions. So yes, so like I said before, if the left side is all oranges, then if you only look at the left side, the entropy is 0, right? If the entropy is 0, it means you have no uncertainty. you're absolutely certain that everything on the left is an orange, right? So I'll explain it in a very intuitive way as well. But we're now going to look at conditional entropy, expected conditional entropy, and information gain. So anyone have any questions up until this point? Are we good to move on? I'll give you guys time to type it out as well. As this workshop, the lecture part would be relatively shorter, I think, because it is a more straightforward concept, but I think it's still good to go through.
Do you need to add some the number of splits in the loss function so that you don't convert it to penalize the fact that you split it data set? Well,
Yep. So it will be considered. So like if you have 7 oranges, right? Oh, sorry. Let's say you have 7 fruits, right? And it's split into 2 fruits and 5 fruits. The proportion will be considered. So don't worry. When I get into a bit more of the math, you will be able to see how it's tackled. Yeah. So can I move on? Are we good here? Okay. So it's just some exercise. I'll just give you guys like 1 or 2 minutes and just calculate these. So by distribution, I mean that one class is 0.5 probability, the other class is 0.5. So yeah, just kind of practice using the formula a bit. But at the end of the day, it's just a plug and chug, right? It's just 0.5 times log 2 base 0.5. Sorry, log base 2 0.5. You add that, take the negative, right? I don't think we have to go through a walkthrough of this, right? It's just plugging in numbers. So we're good? Okay, let's move on. There is a lot on this slide, but I will go through this one by one. The conditional entropy is the entropy when you take a specific path on the split. So on the, oh my, sorry. So on this decision, right, you can agree that 3 of them go to the left, 4 of them go to the right, right? All conditional entropy is saying is that instead of computing the entropy for this group, I'm computing the entropy of this smaller group. That is all conditional means, right? So how uncertain, so we talked about how entropy is uncertainty, right? When you take the entropy here, you're talking about the entropy, sorry, the uncertainty of the entire set. When you split it into a smaller group, you're saying how uncertain is this smaller group, given that we took this path? Does that make intuitive sense of what conditional entropy is? I'll repeat, it's the entropy when you pick when you pick a certain path, right? So here, there are, I think it's a typo there. Yeah. So there are 3 fruits that are more than 6.7, and there are 4 fruits that are less than 6.7. Now, what do we do with this, right? So, like I said before, you will just compute the entropy of this subtree. Does that make sense? Right? So here you have 3 elements, right? Very important here, right? If you have 3 elements, your probability is going to change, right? If you have 1 out of 3 oranges, 1 orange out of 3 fruits, you will use 3 in your denominator instead of 7. Is that clear? Right? So you're going to do the exact same calculation, right? It is the exact same. That is the typo there, but sorry about that. But yeah, we can agree that this calculation it makes sense, right? It's just doing the entropy calculation on the small groups. So you would do the same thing here, right? Now, we have the entropy of these 2 smaller groups. Now, what do we do with these 2 numbers then, right? Because we found the entropy up here. We found the entropy down here and down here, right? But we want to know how we want to know about the uncertainty after we make the split. So we will need to find the average uncertainty after we make this decision. So to find the average, this formula is scary, but don't worry. I'll explain it. So what you need to find now is something called the expected conditional entropy. All this is saying is, let's say you have like some entropy value down here, right? You will multiply that number by the proportion of the split, if that makes sense to you, right? So let's say I have an entropy of 0.5 on the left, right? I'll multiply that by 3/7. Does that make sense? Because that's the proportion of the split that I made when I made that decision, right? You do the same thing, right? If I have 0.5 entropy on the right, then I'll multiply that by 4/7. And I'll add them together, and that will be my expected conditional entropy. Any questions up until this point? Because we will get into some not even, but some heavier math concepts. So it's good that you understand everything until this point. Also, Ria, can I put you on D&D on Discord? Yeah. Yeah.
You're fine. This Windows that's being displayed.
Oh, okay.
Yeah, no, that's fine. Sorry. I'm just gonna quit.
Thank you.
Hold on. Fast pace, maybe I must have done just a little bit, okay.
Okay. Yep, so that was quite a bit. So let's just summarize these concepts before we move on, right? So entropy, we can all agree, is the total uncertainty, right? The data set we have, right? Second of all, conditional entropy, right? What is the uncertainty if we take a specific path of the split, right? And then we have conditional entropy where we just take the sum of them or weighted sum of them. So are those three concepts absolutely clear? Because we will need to be very clear of these concepts before we move on to the final piece of the puzzle. If no questions, I'll give you time to type it out. We're pretty good on time today, so I can take things slower. So are we good? We're good. I'm gonna move on. So we'll just do this calculation that I just said, right? We're just going to take the entropy value we got and we will multiply it by the proportion, right? I am so sorry there is a typo here, but the calculation makes sense, right? Good. So now you might be thinking, well, I have this number now. You might be like, yo, Warwick, right? You're just telling us to do a bunch of calculations. We have so many numbers. What do we do with these numbers? Well, we are interested in knowing when we make a decision, how much our uncertainty reduces. I'll repeat that again. We want to know how much our uncertainty reduces after we make a decision because we want to be more certain about something after we make a decision, right? Or after we make a split, right? So we want to look at if I know feature X, how much more confident am I in predicting this data set, right? So I think the math will actually make you understand this more. So you remember back here, right? With these 7 fruits initially, we found the entropy of the entire set, right? Remember this? And we also found the expected conditional entropy, which is, oh my God, this number here, right? So we're going to define something called the information gain. So information gain, like the name suggests, is how much information you gained. I don't know how else to say it. How much more information you gained. It is defined as the entropy originally subtracted by the expected conditional entropy. Now, how does this make intuitive sense, right? So your expected conditional entropy, right, is how uncertain you are at something after you do the split, right? So this term here is how uncertain you are at something after you make the split. H of y is the uncertainty before you made the split. So to know how much information you gained or how much uncertainty you lost, if that made sense, you would just take a difference of them. Does that make intuitive sense? Don't worry, there's an example coming. I'll let that sink in for a bit. So, any questions? Any uncertainties? Yeah.
Just why specifically the formula P of X times log 2 of P of X? Why not another formula.
The log accounts for the fact that when your probability is 1, your uncertainty is 0.
You could have taken U of x times U of x minus 1 or something like that, maybe.
Yep, I actually don't know the origins behind the log. Ria, do you know? Why did they specifically use log in the
Why log is in the function?
yeah, why they specifically use log and like nothing else?
It's like the mathematical background of that generating concept that I do not accept at all.
Yeah, it's
but,
like
but there's a way to derive that. I think log, like what it does here, it helps limit it in a certain range. You know how like limitation between 0 and 1, it doesn't like let go infinitely like high to infinite below. There is that kind as well, but I might have to double check that. And like, yeah, let's speak about it like there's other sections.
yeah, he'll speak about that as well. So is everyone clear about conceptually what information gain is?
We need to maximize the information gain.
Yep. That is exactly the next slide. So we want to maximize your information gain, right? We want to make a decision that maximizes it such that we are less uncertain after we split our groups. So that yeah. And to actually let you have an understanding of this, I'm gonna let you do an exercise. So for this split, I want you to maybe punch to your calculator to find the entropy before the split, the expected entropy after the split, and the information gain. So let me know if you want me to have the formulas up on one slide when you do this. But going through this example will, I think, explain to you better how information gain works. Yeah, I'll give you guys like 1 or 2 minutes. You don't have to write it down. You can just think about it in your head and try to think about intuitively, what that information gain is giving you. Let me check the people online. Oops. Oops, something seems to be going on with. Oh, it's not on, right? Yeah, what's going on? Huh?
Yeah, you got it.
What happened? Oh, thank you.
So
Yeah, we're good.
yeah, I got the log, don't worry.
Thank you. Okay, so I'll just show the answers. Oh, I don't know why I'm on pen here. Okay, so here's just the numbers. So in this data set, there's 7 points, right? 5 of them are oranges, 2 of them are apples, right? So if you put it into this format, okay, I need to hide this bar here. Hold on. So do we agree with what's happening on this top formula here? Right? There's 5/7 oranges, right? And there's 2/7 apples overall, right? Before the split. Are we good there? The next one, a lot of numbers, right? So this first line is looking at the left split. So on the left, right, there are 2/7 fruits partitioned there. So we have to multiply by that weight. And then there's 2/2 oranges, right? So you will just do the exact same thing with the entropy, but with this specific side. Does that make sense? And you can see here that this top term is going to go to 0. Now, don't worry about the log of 0, okay? 0 times log of 0 is 0. Just take my word for that. Because mathematically, it's because a linear function grows faster than log, but it doesn't matter. But yeah, can we agree that this top line is 0?
When you program this, do you add like a small variable to log so that it's not equal to 0?
The truth is, when you start coding this, there are so many pre-built libraries that can handle this for you. So you'll see it when you start coding it. So like, you know how in PyTorch there is some like neural network functions, right? Like n.linear and n.relu, if you remember. There are similar things that can handle that for you for random forests. So don't worry. So does the second line also make sense to people, to everyone, right? There's this weight of 5/7, because that's how we split it. And there are 3 oranges and 2 apples. So when you sum that, you get some number. And then when you subtract the entropy from the expected one, you get some number as well. Is this page clear? Does anyone have any questions? Okay. If no questions, I don't know why that bar keeps popping up. If no questions, I'm not going to do this because I'm not going to go through basically the same example again. But it's the same idea, right? It's just different numbers, different split. So now you might be asking, in practice, what actually happens, right? Because how are we supposed to decide on, I know it's a pretty jam-packed slide, but in practice, how do we actually decide on which split we're supposed to take on each decision, right? So this is the general workflow of what happens in practice. So first, you just set up your data set, right? You just have your 7 fruits here. Next up, you're going to try, quote unquote, all, aka many. You're going to try many possible splits of the fruits. And you're going to choose the split that gives you the best information gain. Does that make sense? Why, right? You want to find, yeah.
You try all possible splits like this, or also like this, or both?
What do you mean like this and like this?
Like based on one feature, or and the second feature, and then you choose the.
Yep. So it can be based on any feature. So like it's convenient here. We have 2 features, so we only test out weight and height. But of course, in your real life data sets, there's like a million different features. So that's where the resources come in, right? You asked about why we do this decision trees, right? If there's this many features, we want to save resources, right? If we have like 5 billion features on a vector and you put that in a neural network, your matrix is going to be so big that your computer is not going to be able to handle it. But here, you're just doing basic multiplication. And you might have a question as well. What do you mean all possible splits? These are continuous numbers.
I prefer like this.
Yeah. So exactly, yes. So when you let's say I have these fruits, right? And I want to try out all of the weight splits. You cannot physically do that because these numbers are continuous. Usually what happens is you just test at like a jump, right? You can test like 6.6, 6.5, 6.4. Does that make sense? Right? You try like I don't know what word to use, but you get the point. You choose the one that gives you the best information gain. So when you get a split, right, your data set is going to split into smaller parts. Do the exact same thing over and over again. You might be asking, when do we stop? Don't worry, there are 3 entire slides explaining when do we stop. But are we clear on essentially what we have to do as our first couple of steps? Set up our data set and go through like a bunch of different possible splits. Choose the one that gives you the best information gain. Is that clear? Yep. So now you'll be asking, when do we stop the data? Because theoretically, in an ideal world, right, we can just keep splitting this until everything is pure, right? So if you go back to this old slide over here, I have just made it convenient for you guys that everything is pure. But if we have a billion points of data, just imagine how much work needs to go in order to make everything pure. In your worst case scenario, right, you're going to partition it so that each area only has one single point. Does that make sense? That is not only computationally expensive, that introduces overfitting. So how can we tackle this problem in practice? Sorry, there's a lot of slides here. So there are multiple conditions, right? So let's get started. There are usually four conditions at which you stop splitting. First one, if it's pure. If you're lucky enough so that a split is pure, what's the point of splitting it? We have reached a really good split there, so don't split that data set any further, right? If I have a bunch of fruits and on my left split is all apples, don't split it further. We got there, right? So and mathematically, this means your entropy is 0 there. Does that make sense? The first reason why we stop is because we reached a pure group. The second one is also kind of trivial. There's no examples left, right? Let's say I have like 7 fruits again, and somehow on my left side is 7, my right side is 0. There's no point in going in further into the 0 branch because there's nothing there. Make sense? The third and fourth are more important. The third is the depth limit. This is a hyperparameter. So I don't know if they went over hyperparameters in the past few. You've heard of that word, right? Yeah. So sometimes it's going to take way too long to split them until it's pure. So maybe you can, for example, you can set a depth limit of 10, right? If the tree reaches a depth of 10, you stop there. So you might be asking, if I stop there, but if it's not pure, what is the class going to be? Any ideas? So let's say I keep splitting the tree, right? Let's say I reach my depth limit here. Let's say I get a new fruit and it goes to there. What should I predict? An apple or an orange?
The dominant.
Yep, usually you will take the majority group when that happens. So I'll repeat that again for depth limit. So sometimes if you just keep splitting, it's a waste of resources, it's impractical. So if your tree or your branch reaches some heights, you will just stop splitting it and you just take the majority element every time you get there. Does that make sense? And then the last one, the split is not meaningful enough. Now, let's say you're here and you want to make a split, but let's say somehow the best split gives you a garbage information gain of 0.01. There is no point in going any further. You would rather want to use your resources somewhere else instead of keep going in this branch. Does that make sense as well? If the best split is garbage, don't keep going. Any questions before I move on? I think we're good, right? So it's good to understand these fundamentals, and it's going to make more sense once we start coding it as well. So let's just go through an example on inference time. So what's going to happen is, right, you have this data set, and you know how we keep trying to find the best information gain, trying to find the best split. That's how we're going to get our decision boundaries, right? Let's say I have like 7 fruits and I keep trying different splits and I find that 6.7 is the best split. Then that will be my decision boundary. Does that make sense? That is how you're going to build your tree. You find the best split, and that best split is going to become a internal node or a decision boundary. Make sense? And you just keep building the tree recursively, right? With this smaller group here, you would just keep building this tree, keep trying to find the best split, and that would be your nodes. Anyone have any questions about, go on.
Can you come back to the first graph where you showed the splits?
Which one? The one with the highlights, right? This one?
Yeah, the first.
Go for it.
Yeah. No, I just want to see the number.
Yep.
Based on this graph, can we only make our decision boundaries based off of one parameter? Like, can we draw like a diagonal line basically, or does it have to be horizontal?
It does not have to be horizontal or vertical. I just did it because it's kind of hard to draw out and visualize otherwise.
If you have to check like all the possibilities, then like wouldn't it get like really long if you're also checking in terms of 2 or more?
Yep, and that's why the depth limit exists, right? That's why at some point, if it's too long, that's going to take way too long. You might as well not waste your resources there, right? And also, like I said before, right? You don't want to be you're going to be testing a range of values, right? If this jump is like way too small, you're going to take forever, right? So if I'm testing out like the range of height between like 0 and 5, you most likely go like, oh, let me test 0.5 and 1 and 1.5 and see which one gives me a better split. Yeah,
So you can have lines like this diagonals.
absolutely.
Okay.
Because look, right, we are also looking at a two-feature example. So when you have like a bunch of features, right, this is not going to look anything as clean as this, right? Like, beyond 3D is also just beyond a visual understanding anyway.
Yeah.
So yeah, it can be any shape, any like shape or form, like the boundary.
Just have a line like this that splits in two groups.
Yep. So what actually happens is, right, when you go through your decision tree, when you reach a leaf node, you're going to land in one of these partitions. If that makes sense.
It's just with inequalities, if you have only one feature and one inequality, you can, if the inequality is not based on the other feature, you can't have a line. Like if there is only one feature,
yeah,
the inequality, you can't have a line. So
yep, I think that makes sense, right? So any questions again? Any questions on how a decision tree is made? No? Okay, well, on inference, it's just the same thing, right? I started off by going through an example when we do it on inference. But this, to make it clear, right? When we do entropy and all of these mathematical calculations, that is when you build the decision tree. Make sense? Because on inference, aka when I have a new data point, all you have to do is walk through the decision tree. Does that make sense? I build a tree, and then when a new point comes in, I just walk through it. Now, mathematically, this is computationally super, super cheap. All you're doing is comparing if something is larger or smaller. Unlike your neural networks, you are not doing a bunch of matrix calculations, right? Even during inference in neural networks, there is so much math involved, and there is aka so much like hardware usage. So if you want to do something more lightweight, this is a good way to go. Of course, decision trees themselves have a lot of limitations, and I'll hand this off to Riyadh to start talking about random forests. So, anyone have any general questions about decision trees before we move forward? Are we good? Yeah.
Then it's the children known is to that you can classify like into two or more classes, and you can have like two or more.
Yep, absolutely. You can have way more than two features. So height, weight, maybe you can have, I can't think of anything else for fruit. Maybe color. That's not good. Maybe some other measure, right? Maybe brightness of that fruit, right? And your predictions, yes, this can be as many classes as you want, right? Even if you think about fruits, right? It can be bananas, it can be grapes, right? But it's the same procedure, right? You split it and you take like the majority at the leaf, right? When you keep splitting it, let's say there's like three bananas and then one orange, one apple, you take the banana, right? So yeah, good questions. Absolutely, this goes beyond as many dimensions as you want. Question? Oh, okay. So are we good to move on?
Yep, we're good to move on.
Okay.
Hello, guys. So I'll be taking over from this part of the workshop. We don't have too much part left, well, excluding the coding part in terms of the lecture content. But before, let me start by introducing myself. My name is Riyadh. I was also presenting the second week of the workshop for those of you who were present there. I am a co-op student and also, academic director at UTMIST, also an engineering lead. So before we get into the random forest, there was a very good question that was asked. So I did a little bit of research of my own in this meantime, and I'd like to sort of explain you guys why logarithm as a function is being used inside entropy, or like how is it related to entropy. So it was a little bit different than what I thought, but it makes perfect sense, and it's like good mathematical intuitiveness, even though you guys really don't need to know it for any practical reasons of this workshop. but it's like a good thing to, clean up your curiosity. So let's say we have two independent systems. And when I say systems, I mean how many different arrangements can be made or how many different possible states there are. States, arrangements, I'm using them like as a synonym to each other, okay? So if you have system one that has three different possibilities, three different states in there, we have system two, an independent system that has five different arrangements or states in that. And if you want to combine it with each other, how do we go about like finding the combination of system one and system two? How many different arrangements could there be? Yes. Was there?
Or
Not really. So think about it this way: three states for system A, five states for system B, right? And we want to find the total number of possible arrangements that we would get if we combine these two systems. It's 3.5. Oh, so pardon. It's 3 times 5, right? 3 times 5, 3 multiplied, so 15. So this is sort of mathematics, right? Like doing the combinations. But when we talk about entropy is what we call in math extensive property, meaning we have system A, we have system B. System A has its own entropy or how uncertain it is, and system B has its own entropy, how uncertain it is. And when you combine these two things, the entropy of the combination should be addition of the two possible combinations, okay, or the two possible systems. Which is why the only function that performs that turns multiplication into addition is logarithms. So let me show it on the desk. So on the board right here. So this is the possible number of arrangements, right? A times B equals C. And we are saying if we define the entropy of C to be log C, here's what we're going to get. Log A times B, because C equals A times B. And then you're going to be able to open this up and say, this is log times A plus log times B. Right? Just exactly like we wanted. Yeah, just exactly like we wanted. And this allows us to sort of turn the multiplication into summation, which is what we need for the entropy, and it's just the natural property of the entropy to be a sort of summation of two systems, okay? So this is the mathematical background. If you don't entirely get this, I can always help you out with this after the workshop, but this is not 100% required. So let's move on with random forests. And at the same time, I'm going to be checking the time. We have like 55 minutes left, so we're kind of in a good spot. So we talked about decision trees. I'm hoping you guys have a good idea about what decision trees so far, based on everything that was talked about. But there are some bullet points that I want to go through. Decision trees are powerful. They're easy to interpret. They're easy to understand, as you probably saw. But they have one major weakness, which is that they have a high variance. And to define variance to begin with, variance is just a statistical measure of how spread out the data is from the mean. So if you have a graph, think of like a graph, it has a best fit line or mean, right? It's just like one straight line. And you have different data points, which will be our predictions or the results of decision trees. It's going to be all over the graph. It's going to be way too off. It's going to be close to the mean line or the best fit line. It's going to be all over the place if you keep using different decision trees, right? And the reason for that is, well, Warwick was talking about it. Decision trees operate on the splits, right? And the splits, how are the splits determined? It's if X is less than 5, if your age is less than 5, you're going this branch, left branch, and if the age is greater than 5, you're going right branch. So one number could determine which branch you're going down, right? And that one little change in the age, 5 to 6, could result in that like sort of a major split or like major going direction. which is why when you combine all those features and those individual numbers and splits, they really make huge differences, which is why we can make the statement saying decision trees are sensitive to small changes that we make in hyperparameters or their weights, right? So this is exactly what the slide says. Slide says that small changes in data can lead to a completely different tree structure. This means a single tree might overfit the training data. And remember, please, that overfit means that the model would become extremely well fit to our training data set. And the solution for that is that instead of relying on one tree, which might happen to, again, think of the graph, right? In the graph, it's like it just happens to be this one data point that is way too off from the mean. If you happen to get that decision tree outcome or the output, you guys are really way off, right? You are going to be believing, you're going to be convinced that, oh, wow, I made a decision tree, machine learning, it works, it gives me an outcome, but you don't know how off it is. And we know that it is really prone to overfit. So you might be getting a completely like an off, like an outcome. So what we're going to do is instead of relying on one tree and leaving it up to a chance, we will build many trees and let them vote. And I'm going to get to what voting means in this context. This is the idea behind random forest. It's an ensemble of decision trees trained on slightly different subsets of data. Okay, so let's expand that. So what is a random forest? Random forest is a collection or forest of independent decision trees, right? When you bring in too many trees together, they make up a group of trees, and in English we call it forest, and so we do in the machine learning. Each tree is trained on a random sample of data points, right? So we have a training set, we split them into a random subset of the data points, but we also take all the features that we had, right? Like the age, like height, like whatever, X, Y, Z, we also split them into a random subset of features. And each tree makes its own prediction, and the forest final output is a majority vote for classification or average for regression. And let me remind you that classification is working with discrete outcomes, meaning apples and oranges and bananas, right? We have three different outcomes to choose from, limited number of things. You're choosing one of those. And regression is, think of it as a number line. It's all real values, could be anything in that number line. So it's like there are infinite number of possible outcomes that you could get. This is what regression, this is how regression is different than classification. Please go ahead. Majority vote, well, I'm going to come to that. We're going to actually work on an exercise to understand that. But majority vote is basically you have three trees and you have binary classification, A or B, two possible outcomes. Two of the trees are saying the result is A. One of the trees is saying the result is B. So you're looking at all the votes, whichever class has been set by more trees, so it got more majority of the trees, that is the result that we are going with at the end.
But we said earlier that trees can be not 100% sure that it's A or B.
Exactly.
So maybe there's a probability associated to this choice.
Right.
So they're 51% confident that it's A, for example.
Sure.
Do we take
So
do
that
we count this probability?
we don't no, we don't take the probability there. Like we don't really think of the numbers. What we do is, because we said like one tree could be biased, right? Depending on the values. Okay. We want to take just multiple trees together and we want to give each one of them like a say and take this all the outcomes that we have, and whichever one has been said the most, there is a more chance that it is the one that is the correct classification or the correct outcome.
Like if we have two trees that are saying that are 100% sure that it's B, and we have three trees that are 51% that it's A.
Okay, I see.
So
That's a good question, but majority vote doesn't really depend on the probabilities. So they're not kind of tied into each other. I get the question that you're asking. The question is basically if you have two trees that are 100% each and three trees that gives you a probable, like give you an outcome, but they all have like only 51% of confidence in their, outcomes, right? Lower confidence. Why, like, should we go with the three trees that are saying it's B, or should we go with the two trees that are more confident, but they're fewer in size or fewer in the number? And the answer is it's kind of going to be like two different concepts. I'm pretty sure it can be combined together and like could be looked into each other. But like for the simplicity of this lecture, we want to understand this concept separately from that. But there are probably some mathematical calculations that take that into account too when they decide on that. Anyways, this randomness helps ensure the trees are diverse, and this reduces overfitting. So yeah, let's move on. So there is a power in averaging things, right? And the power is that the idea is that individual trees may be noisy, right? But when we average their predictions, the noise, the bias each one of these trees has cancels out. And this reduces the variance while maintaining accuracy. Think of it, again, let's walk with an example, like asking 100 people to estimate the weight of an object. One person might be off, and decision trees could be off, that there's a good chance in that. But the group's average tends to be close to the truth because people will give answers from all ranges, right? From all parts
Yeah.
of range. Yeah.
I think your screen is not sharing.
Oh,
I
it's
just
not.
noticed.
What about?
Like on the Zoom meeting, unless I might be. Oh wait, no, no. Sorry. I clicked somewhere else. Sorry about that.
No problem. Yeah. Okay. Just to continue, random forests use this same wisdom of the crowd effect. So there's a statement about like understanding random forest. It's a good statement. It basically says in machine learning, specifically in this context, wisdom of the crowd is better or smarter than brilliance of an individual. So no matter how brilliant you think your individual decision tree is, the wisdom of the crowd will always outpower that. So let's look at step by step how to train a random forest. Um, so first thing you do is randomly pick a sample with replacement of the training data. And just to sort of refresh your statistics terminology here, picking a sample with replacement means you have a basket with so many papers, right? Each one of these papers is one sample, is one training point, data point, and you want to sort of take a little subset of that whole basket because you don't want to use all the data points there. So you take the paper, you look at it, whatever, you note it down, and then you put back that data point into the basket. So if you take like, with the second attempt, when you're going to go and take it from the basket, you might get the same paper, but that's okay because that's the point of the replacement, okay? So that's what we call bootstrapping and statistics. So you basically choose a subset of the training data set. You grow a decision tree on this specific subset or this sample. And at each split, you randomly choose only a few features to consider. Repeat this process to build many trees, for example, 100, 200 trees. And then when all the trees are done, you're looking at all their outcomes, all of their outputs. If we are dealing with classifications, if they have discrete number or a concrete number of outcomes to choose from, we'll look at all the outcomes and we take whatever is majority. If we have numbers, some real numbers, 5, 10, 13, whatever, 15.5, everything giving like different numbers, we are just taking the average of that. And that hopefully gives us a more stable result. So we can understand the classification case by looking at this example. So it says 3, 1, 3, 2, all the way to 3 n. But think of it like there are 3 trees. So there are only 3 of them, right? Like it's replace 3n with 3, 3, 3. And in this case, they're all predicting some value. What would the majority voting decide on? Just by looking at the example. What would the final class be? B, right? Why B? Because there are two B's and there's one A, so we go for the majority one. So this is an example of classification. In the case of regression, we are dealing with numbers, right? So we don't have specific classes right here, but we can average them. So we have result 10, result 12, and result 17. Try to average them out. Pardon? 13 is the right answer. Yeah. So like this also goes to show how, for example, one outcome can be 10 and the other one can be 17. And you could appreciate how 10 and 17 are sort of like different from each other, right? Like they're far off. But taking the average brings them to a stable result. And again, this is sort of a recap on why randomness helps. By training each tree on different subsets of data and features, each tree learns a slightly different decision boundary, right? So you've gone over already that. This diversity makes the overall model more stable. The key benefit is going to be there's going to be less correlation among trees because our features are random, our training data set is random. So this will lower the variance overall. And the random forest does combine the strength of many weak, unstable learners into one strong and stable predictor. Okay, is everything clear so far? Okay, that's good. So there are some advantages and disadvantages that we can very quickly go over. So I'm not going to like linger on each one of these points, but just to understand the bigger picture, advantages is that it handles both classification and regression. It's robust to overfitting, right? This was the main goals from the beginning. It works well with high dimensional data. It automatically handles missing data and maintains accuracy even with partial data, right? And this is thanks to that bootstrapping part, like choosing with replacement. It can estimate feature importance, tells you which variables matter most, right? Because you're taking into account a lot of trees. And the disadvantages side, we have the fact that it's slower to train and predict than a single tree. Well, obviously because you were predicting 100 or 200 different trees. So like it's 100 or 200 times slower. It's less interpretable. So it's like it's basically a black box because there are so many forests involved. You don't really see how that outcome was achieved because there are so many just like trees and feature decisions that's in play. And it requires more memory and compute. That is for the infrastructure part. And let's talk about ensemble learning now. So just before we start, remember that random forest is just one type of ensemble learning, okay? Random forests are one type of ensemble learning method. Ensemble learning combines multiple models, which we often call weak learners, to create stronger and more accurate one model. The main idea is that each model makes its own prediction, and the ensemble aggregates them in a smart way, combines them in a smart way, right? It could be majority vote, it could be average, it could be something else. So we'll be going over all of them. Ensembles can dramatically improve the performance, especially when individual models have complementary strengths and weaknesses. And one thing I would like to note is that if you guys were to look into like real life applications of machine learning and like if you were to work in companies and whatnot, it's almost very rare that like people use actual individual decision trees because of all the problems that we laid out. If any variation of decision tree is going to be used, it's most probably going to be random forest because random forest is just magnificent from that point of view, right? It's really strong. So bagging is, for example, what random forest is, right? Like random forest falls under this category. Each model is trained on a random sample of data, and it reduces variance by averaging many independent learners. So we went over that. This is one category. There's another category called boosting. In boosting, models are trained sequentially. So each one of the models focuses on the errors of the previous model, and they reduce bias and improves accuracy in that way, right? So you have one model made a decision. The second model takes in the same training data, but it also takes in the outcomes of the previous model, and it tries to understand what the errors there were or like where it was weak, so it improves itself again, and then you keep doing that until model can make the best decision possible. And there are some popular algorithms that are used in the industry. So each one of them has like different features, different back-end like implementations, but all of them are accessible through like public libraries if you want to play around with the interfaces. Yeah. So ensemble learning, this is again the bigger picture. This is actually, well, I say this is ensemble learning, but this is actually an example of bagging. We have training data. There are subsets of training data that has been bootstrapped from the main one. We have base learners, so individual models that make decisions. We have individual predictions coming from those base learners, and then we combine them in a smart way to get the final answer. So this is how bagging works. Exact same thing, just displayed a little differently here. And boosting, which was the other type of ensemble learning method that I mentioned, what it does is there is a training data set. It's a whole training data set. There is no like bootstrapping or anything here. There is one base model that learns and it makes a prediction. The second training data set is combined with those predictions and given to a different model. The model improves itself, and then it keeps going on like that until the prediction is good enough. There's also like another type of ensemble learning method called stacking, which is also kind of smart. Let me actually mention that. I didn't include it in the presentation, but what stacking does is it's actually pretty similar to bagging. So we have bootstrap samples, we have base learners. Base learners output individual predictions. But then what you do is you take those individual predictions and give them to another model. So there's another learner that takes in those predictions and figures out how to get the correct answer based on that in a little bit more complex way. And then it outputs a final value. So it's basically like right at the very last step. So if you guys can see my cursor here, think of it, there is another model, and that model's like operates like with a little more complex system as to decide how to combine these yeses and nos rather than just taking majority of order averaging. Go ahead. There's a question.
Base learners, is it just decision trees or?
Decision trees. In random forest, it's decision trees. In other, I guess, like types of ensemble learning methods, it could be something else. So you could, well, you could like use the schema with, for example, let's say logistic regression, right? If you remember from the second week, logistic regression pretty much does the same thing. It predicts outputs, binary classification, and then just train different logistical regressions and then decides on their individual outcomes on which one is the best. Yeah, but usually we need it with decision trees the most, which is why random forests are so popular, because decision tree is sort of like one of the types of the ML algorithms that is more susceptible to individual variances. So it can like be like slightly off. It can be really spread out, right, in terms of how it behaves. It's kind of weak, right? Yeah, it has a high variance, so that's why we need random forest in this context.
XGBoost? What's the learner? What's the model, the base model of XGBoost?
XGBoost, it basically uses boosting. It's just like, as it's described here, it's an optimized regularized version of gradient boosting. It's faster, more accurate, and widely used in machine learning competitions industry. It's basically implementation of boosting, if that makes sense. Okay. So if you go into like coding, XGBoost is like one of the options that's available to you to use boosting just by, with one-liner code of, okay, train this using boosting. That would be the function to use, or I guess the part of the library. So yeah, again, this is the final points before we dive into coding. The success of the ensemble methods comes from their diversity plus aggregation, the smart way to combine these two concepts. If each model makes slightly different mistakes, that's no problem because the ensemble can average them out. Mathematically, this reduces the model's overall error and improves generalization, which is what we need in machine learning the most. And intuitively, many weak opinions, when combined thoughtfully, become one strong collective judgment. And this principle drives modern high-performance ML systems, from Kaggle competition to production-level AI models and whatnot. So I am hoping these concepts like random forest and a larger scale ensemble learning methods, they are clear to you guys? Are there any questions that I might answer? Okay, sounds good. No questions. What about in the chat? Online folks, let me know if there's anything I can help you out with. Okay. What we're gonna do now is we're gonna proceed to coding. So
Show the screen.
yeah, we're gonna do that, but I want to ask if the people have been shared the link with. Like, have you shared the link with?
Class from last time? You guys remember like the link you guys used last time on coding? Yeah, I'll go around and help, but yeah, just log into the IBM platform and you'll see a week 5.
Yeah, please open it on your end because we're gonna be coding together.
What are you doing?
Yep.
Do you know a specific application where XGBoost is better than neural networks?
XGBoost is better than
Like,
neural network?
recognition, I think.
It has its own like advantages and disadvantages. For example, one thing that is kind of a disadvantage for neural networks is it's kind of a black box. Interpretability of neural networks is quite like it's hard to interpret it, right? Like you don't know how the decisions are made because there are so many circles of like processing being done right back and back. And there's so many layers, so you can't really look into it that much. Whereas decision trees and their group is usually easier to interpret and understand. But they all have like their own weaknesses and strengths. Usually, if you want to decide on like, okay, let's talk about real life projects here. You want to use machine learning, right? You don't know what algorithm to use, so you start with what they call Bayes models. In Bayes models, you don't work with these individual models too much. You don't like hyper tune them or whatever, like I guess like too extensively. And then you just see which one of these separate machine learning algorithms gives you the best result. And then once you see for your specific use case, for the data case that you're dealing with, there is a model that performs the best on them, you just like continue to work with it. So if it's neural network, you continue to work with neural network. If it's random forest, you continue to random forest. And when I mean continue, when I say continue, I mean like keep hyper tuning it, like just making it better, fine tuning it and whatnot. But yeah, it's kind of hard to tell, right? Like is there one model that is better than that, like anything else? There really isn't. There are so many like different use cases and whatever. So yeah, that's why experimentation is like really important in machine learning. Yeah. Anywho, yeah, Warwick, can you help me out?
Oh, for this?
Yeah, like open the
Well, I
code
thought we just
tab.
have this.
Yeah, where's the code tab? Oh, okay. Oh,
You guys, does everyone have it up? You good?
yo.
Yeah. Yeah. Some of it.
Oh no. Your computer.
Oh, shit.
That's okay.
I was wondering why you're like staring at me the whole time. Yeah, here. I should charge this thing as well. The charger. Um, Speaking.
That's okay. Mhm. So let me guys know when you all have your file set up. You access this platform, you can see all this coding exercise on your monitors, and then we should be good to proceed. Okay, is everyone good to go? Nice. Okay, let's start with the so basically what we're going to do here, this notebook contains some exercises on everything that we have talked about. And we're going to sort of practice our skills on coding and just apply this, I guess, like in coding. So with the setup, we are going to import our core libraries like pandas, numpy, whatnot. We're going to bring in our models, bring in utils, matrix, and everything. And then let's talk about the dataset. So for this notebook, we're going to be using Titanic dataset. While the Titanic was one of the most infamous shipwrecks in history, there were certain groups of people who were more likely to survive than others. In this notebook, you will build a predictive model using decision trees and random forests to uh, to find which groups of passengers were more likely to survive. Before we build the model, you will first need to perform some pre-processing on the passenger data. So let's perform the pre-processing. Hold on a minute. I'm sorry, all. Oh no. Okay. Computer stopped working for a second. It was frozen.
Oh, this thing froze.
Yeah. Let's try again. Sorry, people.
Fuck. Oh.
Choose the memory extend to display from.
Oh. I was just setting you up to stable later.
Um,
Wait, Kaden?
hold on a minute. MacBook here.
Yeah, I heard my name.
That's fine.
Well,
Okay, what about okay. You all can see now, right? Okay, I'm sorry. Okay, let's continue. So let's start with the first line. What does this line do? Load dataset basically pulls the Titanic dataset from Seaborn, and drop NA is basically we throw away rows with missing age, not embarked or sex, because we will need those as features. And then we're gonna only keep the columns or features that we care about. They're gonna be survived. They're gonna be the ticket class. They're labeled as PC class. The ticket class is 1, 2, 3, right? Like the higher it is. So for example, class 1 means people who bought the tickets in the highest class, and etc. There's gender, sex. There's age. There is the number of siblings slash spouses that were aboard at the time. There is the number of parents and children that were aboard at the time. There is fare, so the price of fare. There is whether the person was alone or not, and there is whether they were embarked or the port boarded. So these are going to be the columns that we're going to be working with. And the first to do here is, oh my God, the first to do here is gonna be mapping categorical data's string inputs to integers for sex and embarked. Meaning, okay, let's like understand what it means here first. So the color, for example, if there are two options for the colors, red and blue, we are going to map them to 0 and 1. So instead of being represented as strings, they're going to be represented as numbers. But in our case, we're going to do the same with sex and embarked. So for sex, we have two options. The options are male or female. And for embarked, we have three options, S, C, and Q. And for those of you who wonder what those S, C, and Q stand for, those are basically the cities where they were trying to go to in the Titanic, right? Where those were embarked. So destination points. Q, for example, stands for Queenstown. S is like South something, whatever. So these are like three letters for the cities, the capital, the first letters of the cities they were going to. So for sex, here's what we're gonna do. So I'm gonna just use the map function. Male. Oh, and I have to put them in a dictionary. And in the dictionary, I'm just gonna basically map such that male equates to 1 and female equates, sorry, male equals to 0 and female equates to 1. Okay. And then they're enclosed with the curly brackets, meaning they're in a dictionary, and there is another bracket for the function of map. Okay, so what this does is basically it maps them, and we're gonna do same with the embarked df. So you guys already know what I'm doing here. Oh, so I made a typo here. So opening another dictionary, and I'm gonna say, let the city S equal to 1 or 0. Let the city C be equal to 1 and the city Q be equal to 2. Okay. So now after this reassignment in our data set, under sex, we're going to only have 0 and 1s instead of males and females. So all the string inputs are going to be turned into numbers, and the same when embark, and you already know what these mean. And since this is a relatively smaller data set, we can also engineer our own features to include a new column, which would be family size. So give me a second here. So I'm gonna reassign a new feature. Feature is gonna be called family size. And the family size is gonna include the number of siblings plus the number of parents/children. And I'm gonna add 1 here. And the reason that I'm adding 1 is because the family size includes, well, the first column, the number of siblings plus spouses, right? The second column, the number of parents plus children. And the 1 is for yourself. So your family consists of yourself plus all these people. So this is the new column that we have. And okay. Next thing we do is we are basically creating our input matrix, and we are creating our target vector. The difference between, input matrix is it only contains the features that we care about each individual person, right? In this case. And we are dropping survive from that because that's what we're going to be our inputs. And Y is going to represent only the targets, only the outputs that we care about, which is going to be survived. This is what we are trying to predict, if the person survived or didn't survive. Okay, so let's separate them out. And then let's split them, right? 20% of the data set is going to be our training data set, and 80%, sorry, 80% is going to be training data set, 20% is going to be testing data set. And then we're going to be calling this just to see the results. It's not running. I wonder why.
Oh, you want the endpoint is, it's not on there.
Wait. I thought we're working. I thought we're doing this right.
Yeah.
Select. Let's run it again.
I want to see the results for of this. Hold on. Oh, yeah, it did pen. Okay, my bad. Did pen. So we have 569 training samples and 143 testing samples, guys. Now let's move on to the second section. So setting up a decision tree classifier using sklearn is relatively straightforward. However, how you design the tree is up to you and can be done by passing parameters into decision tree classifier. So decision tree classifier basically is a function as interface function that we use to train the decision tree. We don't care how it is done in the background. All we know is the result is going to be the model that we get out of this training sample. And it's going to make all the decisions and all the operations of training a decision tree on its own. And there are some parameters that we can use here. And the parameters are, for example, criterion, right? Like determines how to measure the quality of the split. Remember the uncertainty bit? There is Gini and there is entropy. So entropy is what we learned. There's max depth. So what is going to be the max depth of the trees? Like how many layers or levels are going to be there? Minimum number of splits, minimum number of leaves, max leaves. So there are so many of these, right? And each one of them has a description if you guys are curious. And let me write the code to do this. So I'm going to define a variable decision tree. I'm going to use this decision tree classifier. Random state. So it's basically the number for reproducibility. If you always choose the same seed, it's always gonna basically like use the same random settings. And despite the fact it's not exactly sure what like this random exactly like represents. I think like for example when it chooses like at some points if it has to make some random decision, it's gonna be using this random seed for reproducibility, but not 100% sure. Yeah. But yeah, okay, let's continue. Decision tree classifier. Okay, let's make some space for the arguments. So criterion. Criterion is going to be entropy. Max depth is going to be 5. So we're going to need at least 20 samples to split a node. So that's why I'm doing split min sample split is 20. And then I'm going to say min samples of leaf. So each leaf is going to have at least 10 samples. This is how I'm specifying it. And the random state is going to be equal to 42. Okay. Yep. And then I'm going to run this function with only the training data set. So this is the input sample, right? All the input vectors. And this is, result vectors.
Around this comes from the implementation of decision tree. The algorithm itself is deterministic.
Okay.
But some implementation may have can involve some randomness. That's why we.
Oh, I see. So implementation can involve, but you didn't see what part of the implementation specific.
Liquid splits.
How it's gonna, okay, it's gonna be
Yeah.
random which one it goes. Gotcha. Okay, sounds good. So I'm gonna run this as well, guys. This is the parameters that I get. So everything that I haven't specified in my arguments, they are basically set by default, and that's fine for our purposes. Um, and let's, oh, yeah, sure. Any questions here? Oh, no problem. So decision tree, this is the model. This is the instance of the class decision tree classifier with all the hyperparameters that we specified. We run the fit method or function, and that learns the splits from the training data. Okay. Yeah. So those are basically our first line of defense against overfitting a single tree. Can I move on? Everyone is good there? Okay. Let's look at the random forest classifier now. So we're going to do pretty much the same thing here, except now we are dealing with random forest. Okay. So there are more parameters if you are curious. The parameters are like, and how many estimators, so how many trees we're going to have in the forest. The default is 100, but we're going to use 200 trees. The bootstrap, right? If each tree should train on a random sample with replacement, and the default is true, and that's like the default behavior, so we're going to keep that. So there's like out of back samples for validation, whether we should use it or not, how many like threads it's going to be run on, or like how many parallel jobs will be done at the same time, just speed up the training, and so on and so forth. Okay, so let's go. I'm defining random forest as a variable, and I'm going to use this again class that we imported from the from the library that we used, right? And here is some of the hyperparameters that I'm gonna use. 200. So 200 trees are gonna be inside this random forest. Max depth is gonna be the same as above, so I'm gonna do just 10. There's gonna be only 10 levels at a time. In sample split, it's actually gonna be 10. Samples leaf is going to be 4. This is to avoid tiny leaves. And max features. So I'm going to just explain what this is in a second. It's going to be square root. And what this determines is basically features subsampling per split, or diversity, not a word. Criterion. So let's use a different criterion this time, just to sort of like experiment with the different options we have. I'm going to use Gini rather than entropy. And random state, I'm going to use the same number I used above, which is 42. Okay, so now random forest fit, just like I did above. And I'm going to use the same train data set and same targets that I spared for the training data set. I'm going to run this. Okay, good. This has been run. And let's evaluate the performance. And I want to talk about a little bit performance here because we have different metrics and each one of them is kind of important to know. In fact, like a fun fact, if you guys are, I don't know, like interested in a role that you would be interviewing sometime, there is a good chance people are usually asking about different metrics that you can evaluate the performance of your machine learning models, like in industry, right? Like for the actual job interviews. So maybe take a note of that, or like keep it in your mind for the future. Look it up after this workshop as well, and you're gonna see like it's useful for the future. So 3 different ways we can evaluate model performance: accuracy, precision, recall, and F1 scores. Typically, we prefer to use accuracy when we have a balanced data set, meaning the number of samples we have for each class is the same: 50 true, 50 false, 50 oranges, 50 apples. That's when using accuracy kind of makes sense. The other 3 metrics can be used for both balanced and imbalanced data sets. So they're like giving us a little bit more flexibility here. So the accuracy basically represents the overall correctness of the model and can be found using accuracy score from sklearn. So there's another interface, another public function we can use. We don't have to make all this calculation mathematically ourselves manually. And the point here is we have positives, we have negatives. They're like both of them have like this certain number of them that are true and a certain number of them that are false, meaning they were misclassified. They were classified as false even though they were true, or the vice versa. But we only care about the true ones, and we take the sum of them over everything, all the predictions that we have made, or all the yeah, basically the scores that we have. And as a result, that gives us accuracy. Precision, and these can be again found by using this function use classification report, again from sklearn library. What precision gives us, it represents a number of predicted positives that were correct. So take all the positives, right, including positives that were true and false. We want to use the score when we want to limit the number of false positives, right? So the fewer positives, the more is going to be our precision, right? Because denominator is going to get smaller. And we want to be very certain when, for example, diagnosing cancer. This is one use case of it when using precision makes more sense. And recall, on the other hand, what it does, it represents how many actual positives were found, right? Out of all the positives that we know exist, because when we say false negative, right? If you have two options, if you predicted negative for something and you know it's false, well, in truth, it's actually true, right? So you're taking all the truths that you know exist, and then you're taking true positives out of them. And we want to use the score to limit the number of false negatives. For example, again, there's an example here of the use case for self-driving cars, for example, labeling as many objects as pedestrian, even if they aren't, rather than missing someone. And F1 score, what it does is it basically combines both precision and recall. It takes some, or it takes their multiplication theory product, and then it divides them by their sum, and then it like multiplies the whole thing by 2, and that gives you F1 score. So it's a really strong matrix to look at because it has everything in it. And support represents the number of samples in each class. Now, what we're going to do is we are going to run this because there's nothing to do here. And let's see how did our functions do here. So, okay, there it is. So let's look at the results. So we have training set, we have testing set. Training set, you know the difference between the two, so I'll not go into that. So let's start by only looking at the accuracy. So as we expect, training set for the decision tree is higher. Testing set is a little on the lower side. So this almost implies that there is a little bit of like overfitting going on, right? Because it's more fit to the training set that it was trained on. And when it's, given an unknown testing set for the first time that it hasn't seen, it performs worse, and you can see all the sort of results of the other matrix sort of align with that. For all of them, training set always higher, even precision recall and F1 score, and for the testing set, it's a little lower. So it's not the ideal case. We want to have testing accuracy or testing matrix as high as possible, performing as good as they can possibly be, and training set sort of matching that, but not being like extremely well fit. So let's look at random forest now. So in random forest, you can see, well, there isn't too much of a difference, but you can see testing set has gone up a little bit, right, by 2% or so. But most importantly, when you look at, for example, F1 score, for example, it performs better, relatively better. Yeah. So let's get to the question now. And I want you to think about this question. Looking at the scores above, which metric would you say would you take into account for this data set or task? I hope you guys are thinking about it in the meantime. Yeah. Okay. So by looking at the splits, you guys can tell that there is a mild imbalance. Oh, sorry. Yeah, there's a mild imbalance, and while accuracy could still be useful, uh, to assess the overall model correctness, it is always better to look at the F1 score. So I'll move on that and I'll plot the trees. So there's nothing to do here. All we're gonna do is like observe how the trees were plotted. And then we can talk about the questions. So the question one is when you look at these two plotted results, and you guys can plot them on your like part as well, you don't need to do anything. Which model performed better on the test data, and why might this be the case? And the second question is looking at the three plots, do the splits make sense intuitively or not? So think about it for like a minute or so, and then we're going to answer this question, and then we're going to really quickly do hyperparameter tuning, and this is going to be our last section. And then whatever final questions we have left, you guys can think it after the workshop, or always connect with me. Yeah. So you had the results up here. If you guys followed with me, you guys can guess which one of them like you guys could actually not even guess, like just see from here which one performed better on the testing set. Okay, so you guys can see the generally random forest classifier as we expected, it performed slightly better on the test data. Why? Because it's an ensemble of many decision trees, right? What it does, it reduces the overfitting on the training data. The less overfitting there is training data, the more the testing accuracy is or testing matrix will go up. So they can determine which features are more significant to the final result because you're looking at many trees there. And since the decision trees are limited, they might not generalize well on the test data, just like we talked. And looking at the tree plots, do the splits make sense intuitively? So did you guys like get this plotted on your part as well on your computers? Because I want you to like pay attention to like specific points here, right? Um, you can see, for example, in the decision tree, look at the decision tree only, not random forest. The first split depends on the gender. And we can see that women were more likely to survive because they have like bluish, more blue colors as opposed to men. When it branches off from the men's side, right at the first splitter, it goes like more like dark orangish, meaning they were more likely to die. And this makes sense because like historically in Titanic as well, women and children were a priority for the lifeboats, right? They were saved, I guess, like as a priority first. And you can also see somewhere in that branching that people with higher classes, for example, first class, again, were more likely to survive compared to the people in lower classes, right? First class was again was a priority when boarding lifeboats. So that is there. So as a last thing, what I'm gonna do is I'm gonna evaluate hyperparameters, and I'm just gonna copy paste what I have here because it's kind of a long uh it's kind of a long code and we don't have that much time left. I'm sorry, guys. This keeps going off. Da, 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 da. Yep. There it is. Okay, there we go. Bear with me for a second. Okay, so this is the hyperparameter tuning for our first model. And this is the hyperparameter. So we're going to observe the plots that we get here. And with that, we're going to sort of call an end to it. Okay. There we go. So what we are doing here, we are defining a list of hyperparameters and values that we want to loop through for each model, right? For example, max depth 2 to 20. There are different values. Mean sample split, again, different values. And we're going to loop through each hyperparameter and its corresponding value. You can see within like the first greater for loop, we're going to train a new decision tree for each value and record its training and test accuracy. And then we're going to plot accuracy and hyperparameter value for each hyperparameter and see how it changes or how they impact each other. Oh, okay. I'm sorry. It's kind of weird. I have no idea. Can you take a computer? Your computer.
Oh, mine?
Yeah.
Oh, sure. Oh, I don't have the thing low key.
Yeah, just take it out. Oh. Okay. You guys should be able to see it in a minute. What? Choose content. Window or app. Choose window or app. Mirror this window. Okay, good. So guys, let's look. The more max step increases, training accuracy goes up, testing accuracy goes down, overfitting, right? Classical example of overfitting. In the case of mean sample split and mean sample sleeve, the opposite is observed. So the performance is actually getting better because test accuracy is like slightly, it doesn't go up, but training accuracy goes down, which means overfitting is going down. Here as well, there is some certain point where testing accuracy is the highest. So we're going to be looking at that. 5 is the best. Jesus, just okay. So basically, you got the idea. So I don't want to keep you any longer, and the computer is acting off today. Sorry for that. But I hope you guys could take away some points from today's lecture. And this was a fun workshop for everyone. And yeah, thanks for coming. And we're looking forward to seeing you in the next workshops as well. Thank you.